Hello, my name's Callum Kingstreet and I'm a fifth year chemical engineering student at the University of Edinburgh. Today I'm interviewing Professor Glen McHale, the new Director of Discipline for Chemical Engineering. Please could you give a little introduction to yourself and your background and research interests?
Okay, so my name's Glen McHale. I'm a Professor of Interfacial Science and Engineering. What's my background? I guess I've been around more than 1 or 2 years. I've been in a number of universities. When I was very young, I didn't know whether I wanted to be a scientist or an engineer. I was interested in sort of physics. I was interested in electronics. I actually did an original degree in sort of physics with some electronics. And then I ended up going rather pure and doing a sort of PhD in mathematics, in applied mathematics. And I sort of started a journey over to engineering that went through applied physics and instrumentation, engineering, and I ended up really as a material scientist. And that was my journey. And I guess the reason I did that is I became more and more someone who wanted to solve problems. I looked at the physical world, asked the question, how do we do this? How do we solve this? How do we sort this out? And that was very much where I came from. And I guess that's one of the differences between an engineer and a scientist. Engineers solve problems, and I eventually realized that. And I work more and more with people working on fluid mechanics problems, flow problems, phase change problems, evaporation, condensation, and I guess that's how I came over into engineering here. Prior to being at Edinburgh, I've been head of faculty, I've been a Pro-Vice Chancellor responsible for research, and now, of course, I'm Director of Discipline here at Edinburgh while continuing my research. So that's my background academically.
So what is your research mainly focused on?
So I very much look at how liquids interact with surfaces. So things like water on Gore-Tex, a sort of jacket, or often I look at nature inspiration. So if you look at lotus leaf, for example, why is it you can have a lotus leaf remain dry and clean even though it lives in a very muddy environment? How do you do that? If you look at something like a pitcher plant, an Nepenthes pitcher plant, then this is a sort of carnivorous plant, and ants can walk around its rim, and then they just slide down into the digestive chamber of the plant and they get eaten, if I put it that way. How can it be that the surface can be so slippery to the ant that they can't get grip? So I very much deal with surfaces and how surfaces interact with liquids. In the ant case, they're using oil on their feet to adhere to the surface, and plants have a way of overcoming that. And so that's where I work. And the sort of applications that comes in is if you've got, of course, a ship moving through the ocean, a boat, can you make it go faster with less drag? So, for example, I worked on some work for UK Sport before the London Olympics, trying to tell them whether we could win or whether we might get beaten, so to speak, by reducing drag. You can look at flow of liquids through pipes and tubes, or you can look at droplets on surfaces and how they move around. You think about evaporation, heat exchange, things of that nature. I can sort of show you what I mean if you want. I've got some demonstrations here, so if I pull them over and refocus, I'll give you an example of what I actually mean. I've got a bowl of water here. I've got some different objects. This is Oasis. It's a flower arranging foam. I've got a Harry Potter maze game. I've got some sand. There's magic sand. It's special sand. I've got some surfaces that are made in my lab. I've got some plumber's tape, PTFE tape that you use when you're seeing things. And I've got some paper clips here. I'm going to start with the paper clips. You know paper clips, they're made of metal. Let's have a look at these. And what I'm going to do is I'm going to try to very carefully lower into this bowl of water to see whether it works. And you see that the paper clip is floating around. You can see it floating around. And so even though it's made of metal, and from the point of view of mass and buoyancy, it ought to be sinking, it's on the surface of the water. And so you have a sort of surface tension effect, a capillary effect, surface tension of water. I can put a second one in to see whether I can get a second one to float. Of course, it's not floating in that sense. What it's doing is it's just sitting because of the skin effect of water, the interfacial tension, the surface tension. And in fact, if I take this is this flower arranging foam, and I use some Gore-Tex waterproofing agent. If I now use a sort of spray I can get lots of water just moving around. You can see that's not, that's pretty slippy. The water drops completely ball up. And that's what I do. What I do is beat chemistry, because chemistry can only do what the PTFE does. It can make half things, and I can make water drops ball up and roll across. So they can move very easily on those surfaces. And you can sort of see that here. This is one we did. It's one in the lab. You can see the water drop just come off. This one's actually got a sort of energy well in the center, so the water will gather in the center. It will naturally propel itself to the center. And so you can do water collection, you can imagine. This one, of course, this one here, this is a test whereby you had a drop tube, and we simply drop this in water and let it settle, and we get to terminal velocity, and we look at how fast it goes. Now, when that goes underwater, you may not be able to see, you may be able to see, but what you often see is a silvery reflection underwater. And that's because this coating retains air. And so if you imagine swimming under a pool and looking up at the top of the swimming pool, you'd see a mirror. That's the reflection of the light. And what's happening is, even underwater, that remains dry. Now, you might imagine that if you fall with a bag of air around you, you fall less fast, more slowly, because of the buoyancy. But actually what that air does is reduce the drag, and that overcomes it. And of course, you can use these for all sorts of things. People make tiles on ceiling, on walls. People do all things. But this is one example where you make a very simple game where you've got a maze, you put water in, and the game is Harry Potter game. Just get your water in the center. Instead of rolling a marble, you roll droplets of water. In fact, one of the original origins of these things came from sand. And if you mix sand, normally you're used to the idea that sand will, of course, get damp. But of course, here you can see the water drop just rolling around, and you can see those silver reflections, because actually there's always air underneath. This is what we call the bed of nails effect. So what we make is a really rough surface, like a bed of nails, but we make it hydrophobic, and then the water just sits on the peaks of it, and that's the reason it rolls around. So my research really is about how liquids interact with surfaces, not just water, but oils. It's around how we sort of make liquids move very easily across the surface. It's effectively how we make super water repellent or super oil repellent surfaces. All of that, I guess, is my research. And as it says, it influences a whole set of things, from drag reduction for flow through pipes, through things moving through vehicles like ships moving through the water, through to evaporation, condensation, heat exchange. If you're interested in that kind of research, our research group does maintain a public understanding website called www.naturesraincoats.com, Nature's Raincoats in one word.com, and that's a public understanding website that we first did for the Royal Society Summer Science Exhibition. It explains some of those ideas, and they're linked to bio-inspiration.